Yeah, of course, I can start.
So we have Carlos Munos Royo from the MIT here. And I think you completed your thesis 3 years ago, also at the MIT, and just recently published a paper on what you're going to talk about today. It looks super exciting. So thank you very much for sharing.
Thank you, Sarah, for the introduction. I'm going to share my screen now. And okay. This one here. There we go. Okay, so you should be seeing my screen now. Okay, so, well, thank you first of all for the introduction, Sarah. Today, it's great to be here today talking to the JETZON community. Usually, I know that JETZON talks are mostly focused on biology, but today I'll be talking about our research on understanding and modeling deep sea nodule mining midwater sediment plumes. So I will be talking mostly about physical oceanography and also fluid dynamics. But there is, of course, a clear intersect between our research on sediment plumes and the community of biology researchers. Our aim, the main goal of our work, is to actually develop the tools that then enable to assess the physical behavior and determine the concentrations and the extent of these sediment plumes, so that then biologists can actually use the outcomes from our models to, in the end, assess the actual impact on the biology from these sediment plumes. So today I'll start by giving you an introduction to deep sea nodule mining and sediment plumes, especially for those who are not familiar with the topic. And then I'll talk a bit about why sediment plumes are challenging and why this is still an open research topic, and the reason why I'm talking today here. And after that, we will just dive into the physical understanding, the modeling approaches, and the field studies that we've conducted to better understand how these midwater sediment plumes actually behave. And I will finish with some brief notes on where we are currently now in terms of this physical understanding and modeling of sediment plumes. So I'll start, as you may well know, mineral resources really are abundant in the deep ocean. Currently, there are 3 main types of resources that are being considered for potentially commercial exploitation, and these are namely polymetallic nodules, ferromanganese crust, and seafloor massive sulfides. But today we're here to talk about nodules. So nodules are these rocks with a size between 1 to 25 centimeters, and they contain manganese, nickel, copper, cobalt, and other trace metals. And they're found in abyssal plains in oceans all around the world. And they are just lying on top of a layer of very soft sediment. And I have here, I don't know, I think you may be able to see my video. I have here a sample of sediment taken from an exploration area, from a potential mining, deep sea nodule mining area. And this sediment is, I have here a bottle of water with some sediment at the bottom. And this sediment is characterized by the cohesivity of the particles. This means that sediment particles tend to stick together to form larger aggregates. And this is the reason why when I tip this bottle, the sediment is kind of behaving like a gel. But of course, if I shake it, I'm able to break all those aggregates and get all the sediment in suspension. So there are many reasons why nodules are bringing so much attention in the last few decades, and one of them is the vast amount of resources that are currently available in the deep ocean. So for you to have an idea, in the 300-kilometer fracture zone, which is this area in the Pacific Ocean between Mexico and Hawaii, there is more manganese, nickel, and cobalt than in the currently estimated land-based resources. So let's take a look at how a nodule mining operation looks like. So this is a nodule collector vehicle being deployed from a nodule mining vessel at the ocean surface. At the front, the vehicle has a nodule collection system that consists of a number of water jets that basically inject water at high velocity to pick up the nodules. But apart from the nodules, they also pick up certain amount of this seabed sediment. And as they don't really want that sediment, most of it is separated from the nodules in the collector vehicle itself, and it charts right at the back of the collector vehicle, as you see in this animation, creating what we call the collector sediment plume. This is a sediment release that happens close to the seabed in the abyssal plains. So the rest of the remaining fraction of the sediment is lifted up to the mining vessel together with the nodules, and there the nodules and the sediment are separated, and the sediment together with the water and some very fine nodule particles, which are the result of the erosion of the nodules as they go up, are discharged return back to the ocean. And in this case, in this animation, we have a discharge in the midwater column of the ocean, but the reality is that it is yet not clear at which depth these sediment plumes may be released, may be discharged. So we have two main options. The first one is what we will be talking about today, which is a midwater column discharge. So the sediment is expected to potentially be discharged at a depth probably greater than 500 meters. Some other places they are talking about depths greater than 1,000 meters, but that's still to be defined. And the one potential alternative would be to discharge this same sediment closer to the seabed. But as I've said, it is still unclear what will be the final solution that will be adopted. So today we'll be talking about midwater column discharge sediment plumes. So let's start first talking about why these sediment plumes are relevant. And to do that, we need to differentiate the direct and the indirect environmental impact associated with nodule mining activities. The direct environmental impact is caused by the collector vehicle itself, by just driving on the seabed and picking up the nodules, which constitute the hard substrate, and also remove part of the top seabed sediment layer. But as we've seen in the animation, the sediment is then discharged back to the ocean, and the ocean currents transport these sediment plumes away from the mining area, creating what it is known as the indirect environmental impact. So that sediment is creating an environmental impact away from the actual mining area. So the question we're trying to answer is how far and in which concentration do these sediment plumes actually travel, so that we can better assess the extent of impact of this type of nodule mining activities. And the challenge comes when we start thinking about the length and time scales that are relevant in this problem, because we need to study and understand the behavior of micron-scale sediment particles, but we also need to consider larger-scale flow features like mesoscale eddies, which may have typical length scales of about 100 kilometers. So right there in this problem, we have over 11 to 12 orders of magnitude involved. And we have a similar situation with time. We have very fast turbulent processes that happen close to the discharge of this sediment plume. But we also need to consider the overall duration of these nodule mining operations, which may last for about 20 to 25 years. Therefore, as you would expect, there is no numerical or analytical model that is actually able to resolve such a wide range of time and length scales. And therefore, all the previous modeling attempts have had to compromise in different ways, either using low temporal and spatial resolutions, or making some strong assumptions on the initial conditions, on the source conditions of this discharge. And therefore, this is the main reason why we've decided to shift to what we call a multi-scale and multidisciplinary approach. So here we recognize that we need to identify and understand the relevant length scales and use appropriate models to study them, and then put everything back together to actually be able to get the overall picture and have a good understanding on how these plumes behave. And a key component of this approach is to conduct large-scale field studies in which we release sediment plumes in the same dynamic regime than what is expected for a commercial operation. So we've conducted 2 large-scale studies. One was the plume field studies, in which for the first time we discharged a sediment plume using actual sediment from a nodule mining area in the Pacific Ocean, and monitored it in order to validate our modeling approach. And I'll be talking a bit more about those experiments. And more recently this year, we were also involved in the field studies of the sediment, the collector sediment plume, so the actual sediment plume that is discharged by the collector vehicle very close to the seabed during the technical trials of a nodule prototype collector that was tested earlier this year in the Clipperton fracture zone in the German and Belgian exploration areas. So let's start talking a bit more about how we think about these sediment plumes and how we can model them. And first, I want to give you a better idea of what this multi-scale approach means. So basically, now we start just talking about these midwater plume discharges. We identify 2 very different regimes. Initially, very close to the discharge, the plume has this what we call dynamic plume regime, in which buoyancy and, in some sense, the initial vertical velocity and vertical momentum of the discharge are the ones dominating and controlling the behavior of the discharge. And the physical processes and the forces involved here are totally different from those involved in the subsequent ambient plume behavior. So at some point, this dynamic plume, and we'll see this in more detail later, transitions into an ambient plume behavior in which the ocean currents are transporting, affecting away the sediment. The ocean background turbulence is continuously mixing the sediment plume with background ocean water, and that results in a continuous decrease of the sediment concentration. And at the same time, of course, we have the sediment particles settling down because they are denser than the background ocean water. So basically, we need to first get a good handle, a good understanding, and develop the modeling capabilities to be able to assess and understand what happens in the dynamic plume regime, so that then we can use that to inform and to set the source conditions of a larger scale ambient plume model, as it is the case of the figure that we have here at the right hand side, where we have a numerical. This is from a numerical model of a region of the ocean in the Pacific, and we are using actually the dynamic plume model to set the source conditions of for this ambient plume. So let's take a close look at how plumes behave close to the release point. So basically, we're considering the discharge of a sediment-laden fluid that initially has some vertical velocity and vertical momentum going down, and it also has a negative buoyancy. So the sediment-laden fluid is denser than the background ocean water. This results in this sediment plume continuously going down, increasing in depth. And at the same time, because of the turbulence nature of this discharge, there is a lot of mixing, a lot of entrainment, what we call entrainment of background ocean water that mixes with the sediment-laden fluid that has been discharged. This results in a decreasing concentration of the sediment in a relatively short time and length scale within this dynamic plume regime. So as you may know, in the ocean, the ocean water, the density of the ocean water increases with depth. This is what we call the ocean stratification. So because of the buoyancy of the initially negative buoyancy of the plume keeps going down until it reaches what we call the neutral buoyancy level. So at that point, our sediment-laden fluid has the same density than the background ocean water, but it still has some vertical velocity, vertical momentum. So it overshoots, it goes beyond that point, it goes deeper than that. But at that point, it starts being positively buoyant, so it slows down and it kind of rebounds to transition and to reach this final neutral buoyancy depth that we have here, and to transition then into the ambient plume phase that we've been discussing. So the main implications from this behavior is that the initial conditions of the ambient plume, which in the end is what we care about, because this is what the ocean currents will transport away from the mining area, are basically set by how much sediment and nodule fines are discharged into the ocean, and also are influenced by the background ocean stratification, as I've said, by how fast the density of the background ocean water increases with depth. And the main result of this is also that there is no influence from the initial volume and momentum fluxes. So this means that if we are discharging a certain amount of sediment in terms of kilograms per second, let's say, it doesn't really matter if we discharge it very concentrated with not so much water, or if we discharge it initially much more diluted with a significantly higher water volume flux. In the end, the initial ambient plume conditions are going to be pretty much the same. And the good news here is that there are very well established models that have been developed in the last decades in the fluid dynamics field for different applications to study the charges that have this type of physics involved. So this type of models and the underlying assumptions, some of them have been validated mostly in laboratory studies, and also in some cases in some larger scale field studies for specific applications. But there was no previous validation of this type of models in the exact same dynamic regime than what we expect for a nodule mining operation, and using actual cohesive sediment from a nodule mining area. So this is what we did in collaboration with the Scripps Institution of Oceanography and USGS. We went out to the Pacific Ocean aboard research vessel Sally Ride and conducted large-scale field studies of these plumes to observe and monitor them in order to first validate our dynamic plume models, and then to also assess the impact, the effect of the cohesive sediment on the overall behavior of these dynamic plumes. Was recently published, so you can look at our review. So, as I've said, the most relevant aspect and a nice thing from the fluid dynamics is that we just need to make sure that our discharge was in the exact same dynamic regime than what it is expected for a commercial operation. So we can make sure that this is the case by just making sure that these three non-dimensional numbers, like the Richardson number and the buoyancy number, are in the same regime, indicate that we are in the same regime than what we expect for a commercial scale reference plume, which is what we have in this column. So then, based on those parameters, we're able to set the discharge conditions of our sediment plume. And if our models are doing a good job for our experimental plume, we are certain that they will do a good job for a commercial scale discharge, because we are making sure that we're in the same dynamic regime and the relevant physical processes are present in our experimental plume. The next thing we did was to design a plume creation system, which consisted of 2 large tanks and 2 pumps. And this enabled us to have a good control of the initial conditions of the plume discharge that we were conducting at that time. Regarding the instrumentation for the dynamic plume, we relied on 3 main instruments. First, we had an epsilometer, which is a fast vertical profiler that was going up and down about 30 meters away from the discharge. This profiler was developed by Scripps Institution of Oceanography by the group led by Professor Matthew Alford. And on it, we had a CTD and optical backscatter sensor to detect the sediment, and a fluorometer, because on all our discharges, we were also adding rhodamine dye in order to trace the water. So that way we were able to independently track both the sediment and the water that was being discharged. And we also had a turbulence sensor. We also had on the ship an ADSP to monitor the ocean currents, and a phase array Doppler sonar, which is also an instrument developed by Scripps. And it allowed us to get these data sets, which are basically acoustic images of the plume discharge. So we were getting this data on real time. And what you are seeing here in the vertical axis, you have depth, the horizontal is the horizontal extent, and the color map corresponds to the acoustic backscatter intensity. So these dots that you see at the top are the reflections from the connectors of our discharge pipe. And then here is where we start seeing the actual plume going down this green signal. And for example, in this data set, we clearly see how the plume was actually rebounding from this maximum depth as we were describing earlier. So on top of those, we have these black lines, which are predictions from our dynamic plume model, which fit very well with the field observations. Then the epsilometer, the vertical profiler, and I want to recall you that the epsilometer was profiling right around the transition between the dynamic plume and the subsequent ambient plume. So it was at a very interesting spot for us. And because we basically want to be able to set the source conditions, the conditions of the ambient plume at that point. And with that, we were able to clearly see the salinity and temperature signal of the plume at that point. In this case, from this experiment, we were seeing the plume going between 67 to about 79 meters of depth. We can translate that into density and buoyancy frequency signals. We also had the turbulence, and key observation here is that the turbulence at that stage of the plume in the transition between the dynamic and the ambient plume phase was still pretty high. And a very interesting one is the signal from the optical backscatter sensor on the fluorometer. So this is telling us basically the concentration of both sediment and tracer that was observed during that cast. And basically, the key outcome here is that both signals are perfectly aligned in the vertical. So this is telling us that the sediment was behaving as a passive tracer and was remaining in suspension together with the fluid, with the actual water that was discharged as part of these plumes. And this is again, this is validating one of the key underlying assumptions of the dynamic plume model, which is this assumption of the sediment behaving as a passive tracer. After discharging the sediment plumes, the sediment plume for about 45 minutes, we stopped the discharge and we started tracking the plume based on the direction of the ocean currents and the observations from another profiler that we were using, again equipped with an optical backscatter sensor and a fluorometer. This is a top view, let's say, of the track that we were doing with the ship. So the gray line is what we were doing with the ship. We were sailing slowly while profiling the water column. And the red dots correspond basically to positive detections of the plume, and the blue dots correspond to points where we were not actually detecting the plume. So we're basically conducting different transects along and across the plume to get an idea of how it was evolving with time. And the results from all this tracking, we're tracking the plume for over 6 hours, are these two plots that you see here. So at the top, well, in both cases, we have depth in the vertical axis and time in minutes from the start of the plume release in the horizontal axis. And the color map up the top corresponds to the tracer concentration, and the one at the bottom, the sediment concentration. And a key observation here is that both plots have the same features. So we're basically seeing the sediment doing the exact same thing as the water that was part of the plume that we discharged. And this is basically consistent with very slow settling velocities of fully disaggregated sediment particles. So what this is telling us is that this aggregation process that I talked about at the beginning, that these sediment particles tend to stick together, is not really relevant for these type of discharges in this specific dynamic regime. Initially because of the high turbulence, and after that because of the low concentration, particles do not really form large aggregates with high settling velocities. And this is what we are observing here. So overall, through our large-scale field studies, we were able to validate our dynamic plume model and some of the key underlying assumptions. we observed that sediment aggregation was not relevant in the case of this type of plume discharge. And we were also able to test our dynamic and ambient plume monitoring system successfully. So coming back just briefly to the modeling, now that we validate this dynamic plume model, now that we have a good idea on how to model these sediment plumes very close to the release, we're able to set the source conditions for the ambient plume and use that to force larger scale numerical ocean simulations as the one that we are seeing here. This is a simulation that is part of our recent publication, and it was conducted by researchers in Belgium at IMDC. So two key take-home messages are that first, the aspect of the plume is this elongated shape plume that is being transported away from the mining area by the background ocean currents with a decreasing concentration. So the different colors correspond to different sediment concentrations. The background ocean turbulent processes keep mixing the sediment plume continuously with additional background ocean water, and therefore the concentration decreases as the plume travels away from the mining area. Of course, the shape of the plume is determined in some sense by the background ocean current. So, for example, in this one, for a while, the dominant current direction was going to pretty much to the northwest. But at some point during the simulation, there was a shift on the ocean current direction, and that's why you see the shape of the plume changing because of that. And the second key message here is the relevance of threshold sediment concentration values. So basically, this light blue contour corresponds to for this specific case study with the initial conditions that we were using, corresponds to a sediment concentration of about 20 micrograms per liter, which is more or less very similarly close to the ocean background total suspended solid levels in this region of the ocean, which is typically between 10 to 20 micrograms per liter. Therefore, if from a biological perspective, it is considered that anything above background levels is impactful for the environment, this would actually be the area, the extent of the impact by these sediment plumes. And we can see these values with some numbers, with some more tangible numbers on this plot at the bottom, where we see the horizontal area for the different contours that we see in the plot at the top throughout the 90 days of the simulation. So if we consider that that's the threshold level that is applicable for this type of sediment plumes, during our simulation, we were observing that the area affected by that concentration or higher may reach values of up to 1,000 square kilometers under these specific circumstances, and also the specific parameterizations that we were using in the model. Of course, if it is considered that, for example, 4 times above ocean background levels of total suspended solids is acceptable for the environment, and that's considered to be impactful for the biology, the extent of the plume decreases dramatically from this light blue area to this darker blue area. And as you see in the plot where we have the horizontal area, we don't see more than 200 square kilometers being affected by a sediment concentration higher than 4 times the background ocean levels. But as I've said, this is for this specific case study, and of course there are assumptions in there that may need to be revisited. Then, of course, as you see, this is just a 90-day simulation, and we've said that these operations are expected to run for about 20 years, and therefore we cannot really extrapolate much from these short-term simulations. And this is why we're currently working on analytical modeling approaches that allowed us to actually compute long-term impact metrics, such as, for example, the total volume of ocean water affected by a certain threshold sediment concentration throughout the 20-25 year duration of the operations. And that's what we are working on now, and hope to get published soon. So just to wrap up, basically throughout the presentation, we've seen that, yes, we know how these midwater sediment plumes behave. We've been able to validate the dynamic plume model, what happens very close to the charts, and we developed the capabilities to model these ambient plumes in a larger scale, spatially, and also temporally, thanks to analytical modeling approaches that we are working on right now. But of course, as I've said, we need to know the specifics of the operation that is going to happen, and there are still lots of engineering and technical parameters that have, and design parameters that have a lot of influence on the initial sediment discharge conditions, such as how much sediment is going to be discharged, what is going to be the discharge depth, and all that needs to be factored into our the tools that we've been developing. We also need to get more data about the ocean turbulence, which is scarce in this area of the Clipperton fracture zone, and especially in the midwater column. And as I've said, we also need to have a better understanding of what a sediment concentration that is considered impactful, and what is this threshold level, which in the end is what sets the actual extent of the impact by these sediment plumes. So that's it from my side, and I'm happy to take any questions.
Brilliant. Thank you very much. That was super interesting. It looks like a really fun experiment. So well done for pulling that one off. We're really a bit short on time. So if we have a quick question, please raise your hand. And otherwise, I would suggest we move on to Melissa. Do I see? Yes. Oh no, Lisa is clapping. Yeah, we have one hand, two hands. Yeah. I can't see who raised the hand. May you please? Was Tyson? Yeah.
Hello.
Please,
Hi. Yes. Can you hear me?
Yes, perfectly.
So, yeah, this is a great study here, validated, with this instrumentation. And I understand the instrumentation for monitoring the plume is also newly developed. It's state of the art. Could you tell us a little bit more about that instrumentation and maybe kind of what it is? And then the other thing is midwater plumes are probably the most difficult to model, but have you guys already accomplished modeling of the plume at the seabed, or is that not important to monitor that one?
Yeah, good, very good questions. Thanks so much for those. So first, on the instrumentation side of things, for the specifics of our experiment, and we use some relatively advanced and very sophisticated sensors developed at Scripps, as for example the phase array Doppler sonar and that kind of thing. The reality is that was useful for our field study and for what we wanted to actually observe and monitor in order to validate our models. If we think forward in terms of like monitoring these sediment plumes during a commercial operation, if it ever happens, most of the instrumentation that we can rely on is pretty well established, because in the end we need to look at sediment concentrations, which we can do with optical backscatter sensors that are readily available, and there are commercial instruments for that. Probably the more challenging part of this is the turbulence measurements. That there are a few commercial instruments already available, but those measurements are a bit tricky to conduct. There are different techniques that we can use to get that data, but it's a bit more tricky. And yeah, so I think that's pretty much it. Then we use all other very standard oceanographic sensors like conductivity and temperature sensors and others like that. And on the other question regarding the collector sediment plume and what happens to the seabed, we've indeed been developing our modeling approach for those as well. Today, we're just talking about the midwater plume because, well, the JETZON is focused on the twilight zone, and the most relevant aspect was to talk about the midwater column. But yeah, we are working on that. We'll have publications that will come very soon, and yeah, we're working on those and making good progress. So we hope to get things out very soon.
Brilliant. Thank you very much, Carlos. That's great.